Hello everyone, my name is Johannes Eskilt. I am a PhD student at the University of Oslo, and I will today be talking about cosmic birefringence. I will give you guys an update on recent measurements of cosmic birefringence in the Planck and WMAP datasets. I will be mostly talking about the stuff that I've been working on the past couple of years, but you should also check out the video from my collaborator, Patricia Diego Palazuelos, as well. She's giving a talk at this conference. So yeah, you should check out that video. So first of all, a birefringent material is a material that causes the plane of linear polarization to rotate as it propagates through the material. And you can also get a similar effect by sending linear polarized light through magnetic fields. And this is called Faraday rotation. And so the question that me and my collaborators have been asking ourselves, is the universe birefringent on a cosmological scale? Or said differently, is vacuum weakly birefringent? And if it is, and we can rule out Faraday rotation from magnetic fields, which I will talk about later, and then that means that we have new parity-violating physics beyond the standard model of particle physics. And so it's a way to probe new physics. And since the CMB is the oldest polarized light in the universe, it's therefore a very good probe of measuring cosmic birefringence. These are photons that have been traveling for 14 billion years. And so we can therefore see if their linear polarization has rotated, as you can see in this diagram, from mostly E modes into something that looks more like B modes. And spoiler alert, my collaborators and I think that we're finding a weak evidence of this in the public Planck and WMAP dataset. And we're also pretty much ruled out Faraday rotation as a cause of this signal, which means that if this is actually true and cosmic birefringence is real, that means that we have found physics beyond the standard model of particle physics, which is why we are very excited about this result. So yes, I will be talking about that result and how we get, how we derive that result. So first I have to talk about how CMB people measure or talk about linear polarization. So we take the Stokes Q and U parameters of the CMB, and then we do some math to it to turn them into E and B modes. And the CMB is mostly made out of E modes and very little to no B modes. The E modes, they have this kind of pattern. They are parity even. If you look at them through a mirror, they look the same. The B modes, on the other hand, they have this pattern, and they are parity odd. If you look at it through a mirror, it switches side. And the way we quantify the amount of E and B modes are through power spectra in harmonic space. So here you can see the EE power spectrum of the CMB as measured by Planck. This is plotted as a function of the multiple, angular multiple here on the x-axis. And then in addition to that, you can, of course, also try to do all the other possible power spectra, the BB power spectra, the temperature cross E, temperature cross B, and E cross B. Those are the other ones. So if we have a cosmological model that is parity symmetric like lambda CDM, that means that the EB and the TB power spectrum they have to be zero. While if you have a cosmological model that is parity violating, that means that these two power spectra can be non-zero. And so throughout this talk, I will mostly be talking about the EB power spectrum and try to measure cosmic birefringence through that. Because if cosmic birefringence is real, that means that the EB power spectrum of the CMB is non-zero. So the way to measure cosmic birefringence, if you have perfect instruments and no galactic foreground, is pretty straightforward. What you do is that you take the intrinsic E and B modes of the CMB, you rotate them into the observed E and B modes today by this rotation matrix here that's a function of the cosmic birefringence angle. And if you take this equation, you can derive this power spectra equation down here. It also includes the intrinsic EB power spectrum of the CMB. That means the correlation between the E modes and B modes of the CMB. But as that's not predicted by lambda CDM, we set that to zero. And then you have this equation here. You have everything you need to then measure this beta here. But the world is not that simple, and the biggest problem with this is that you have miscalibration angles, and these are perfectly degenerate with the cosmic birefringence angle. So what that means is that if you measure this linear polarization here of incoming light, but the actual linear polarization is this line here, you're off by alpha degrees. So basically you're measuring the wrong wrong polarization angle. And every CMB experiment tries to make sure that their alphas are as small as possible, but there will always be some miscalibration angle. You just want to make sure it's as small as possible. And the other problem is the galactic foreground. We CMB people want to look at the CMB, but instead we are stuck with the Milky Way in the middle here. And it's dust emission and synchrotron emission that's bothersome for cosmic birefringence analysis. So just a bit more on the miscalibration angles. People have been trying to measure cosmic birefringence before, but as I said, it's perfectly degenerate with the miscalibration angles. And so all of these experiments have just been measuring the sum of the miscalibration angle of their instrument and the cosmic birefringence angle. And if they cannot guarantee that their alphas are small, they cannot claim to have a detection of beta. So this has been the main limitation of cosmic birefringence searches before. Then a new method was developed by Yuto Minami and others, and their assumption is simple. Cosmic birefringence has a negligible impact on foreground polarization, and it only significantly impacts photons from the CMB, who have traveled for 14 billion years, while polarization from the Milky Way have been traveling 100,000 years. So you take the observed EMB modes today and you decompose it into the foreground rotated by miscalibration angle plus the CMB photons rotated by miscalibration angle and cosmic birefringence angle. And with this equation, you can derive this equation down here. You have everything you need in the first line here. You take a map of the sky from Planck, for example. You calculate the EB part spectrum, the EE, the BB part spectrum. You take a Boltzmann equations solver and you calculate the EE and the BB of the CMB. And then you're left with trying to measure one cosmic birefringence angle and one miscalibration angle, if you look at one frequency band. So yeah. The problem is, however, that you're left with this term down here. You need to know what the cross correlation between the E modes and the B modes of the foreground emission. And that one is a great source of headache because we are dealing with dust and synchrotron here, and EB of dust and synchrotron has not been directly measured. For dust, there's a lot of evidence that it is non-zero, but people are not sure exactly what it is. While for synchrotron, it's also been found to be consistent with zero, but no one has argued for why it should be non-zero. But yeah, I'll come back to this later. So yes, I remember 7 weeks into my PhD, this paper came out where Yuto Minami and Eiichiro Komatsu said that they had found a 2.4 sigma measurement of a non-zero cosmic birefringence angle in the Planck 2018 dataset. And I remember that was very exciting. A lot of people talked about that. The initial response was skepticism because 2.4 sigma isn't high enough to convince anyone, but even though it is exciting. And the other initial response was that we don't understand EB of the foreground well enough. It could be that the lack of this, because they didn't explicitly include it into the equation, if they made a wrong assumption on this, then that could bias their beta. Even though they argued that it probably shouldn't matter that much for dust. So that's when I got involved in the project. I joined a small collaboration of old Planck members and Yuto Minami and Eiichiro Komatsu. And we used the Planck data release 4 rather than 3 that they used, and we did and that data set has a slightly higher signal to noise. We did exactly the same as them, and by excluding the EB of dust in the equation, we got a higher statistical significance. But there are many arguments that you need to take EB of dust into account, that it is non-zero. And so we applied a dust model that was inspired by Clark and others. And the assumption is pretty much this equation here, where the EB of dust has not been measured. We assume that it's proportional to the TB of dust divided by T of dust multiplied by E of dust. And all these have been measured by Planck. And by including that model, that actually increased the statistical significance of cosmic birefringence. And it didn't go away by including that dust model. We also tried a different approach to model the dust EB, and you should watch Patricia's talk on this. She will be talking about the way she modeled dust EB. But the bottom line is that both approaches gave us a positive cosmic birefringence angle. Yeah, and you should watch Susan Clark's talk on dust polarization here at this conference if you want more detail about dust polarization. Yes. So then we asked ourselves the question, what happens if we include all the Planck maps? So far, we have only included the high frequency instrument of Planck. These are these 4 bands you can see here, and they're dominated by thermal dust. We also, so far we hadn't included the low frequency instrument of Planck, which was developed by a different team, calibrated by a different team. And these maps are dominated by synchrotron instead of thermal dust. And as I said, synchrotron EB has been found to be consistent with 0. So it will be very interesting if we can find the same signal in these maps, because then you cannot blame just dust EB, for example. So we tried that. We also asked ourselves the question, what is the origin of the signal if this is actually a cosmological signal? We can learn more about it by looking at the frequency dependence. For example, an axion-like field that couples to electromagnetism will be frequency independent at the rotation angle. While for Faraday rotation, you will get a rotation angle that is proportional to 1 over frequency squared. And then you have all sorts of crazy quantum theories that predict some kind of integer power. So this is the result of that. First of all, by adding these synchrotron-dominated LFI maps that increase the statistical significance of cosmic birefringence. In black here with the error bars, you can see the birefringence angle if you measure it individually for each of the frequency bands. And you can see that for the low frequency instrument where synchrotron dominates, there seems to be a hint of something happening here, which you cannot blame on dust EB anymore. And then we also looked at the frequency dependence, and we found a number that is very consistent with 0, which is exactly what you would expect from an axion-like field. And it also highly disfavors Faraday rotation cosmomagnetic fields, which means that if this is cosmological, it's new physics, which is exciting. We then added WMAP as well, and now we have included all the public full sky maps of the CMB. WMAP is mostly dominated by synchrotron emission, and once again, by including it, it increases statistical significance. So every time we add new data, it increases the statistical significance of the cosmic birefringence angle. And here, here is the averaged EB power spectrum of Planck and WMAP, here in black with the error bars. And you can see that cosmic birefringence fits this very well. Which, yeah, it fits it very well. And the residual here is consistent with 0. We then also tried to measure cosmic birefringence in the Cosmoglobe map. So Cosmoglobe is a project developed by my colleagues in Oslo. They have been reanalyzing the maps of WMAP and LFI from raw TOD to frequency maps, and they have been able to fix long-standing issues that the official WMAP and Planck teams were not able to fix. So these are the best WMAP and LFI maps in the world, and they also give us a better control over systematics. So now that we have the world's best full sky synchrotron maps, we can then try to measure cosmic birefringence in them. By only measuring cosmic birefringence in the WMAP and LFI maps, because just to say that HFI is not included in Cosmoglobe yet. By measuring this in WMAP and LFI, we get this result here. And one of our main results is that systematic error bars, which we did not have access to earlier, that they are much smaller than the statistical error bars, which is good. But if you only look at WMAP and LFI, the total error bar is still is quite large. So we also included the cross power spectrum with the official HFI Planck maps. And then we only tried to measure cosmic birefringence in the synchrotron dominated maps. And by doing that, we ended up with a 1.9 sigma measurement of cosmic birefringence. So There is for sure a signal in the synchrotron dominated channels as well, not just the dust channels, which is interesting. And that is the current status. We have the past 3 years gone from 2.4 to 3.6 sigma. We are finding the signal in both dust and synchrotron dominated maps. And instrumental systematics seem unlikely. You should watch Patricia's talk. She has done a lot of great work on exactly this for the HFI maps. And the signal seems to be frequency independent, which means that if this is cosmological, it is very likely to be an axion-like field that couples to electromagnetism. And then the big question is, when will we know if cosmic birefringence is actually real or not? When will the statistical significance improve or worsen? And that is when we get better calibrated data. And BICEP3 have been able to calibrate their miscalibration angles very, very well. And you should watch James Corneliussen's talk on that. But the idea is that they are able to guarantee that their alphas are very, very small, so that they just try to plot the EB power spectrum. And if they can get the positive EB and guarantee that alpha is small, then that's it. Then cosmic birefringence must be real. There's nothing else that can do it. And so my collaborators and I are very, very excited to see what they find, because that method is so much better than using this estimator. Because with the estimator, you have to worry about foreground EB, which is a great source of uncertainty. And we're also telling other experiments to also please focus on calibrating your instruments well. Make sure that your alphas are as small as possible, because then we can check if cosmic birefringence is at a 0.34 degrees. Yeah. So yeah, that's it. That's all I have to say. Thank you so much.